So, welcome everyone to this first online meeting for 2017 for multivariable calculus. So, this is very early on in the session. So, where I'm normally what I would do for this sort of stuff is I'd encourage you to ask questions beforehand and to look at some of the questions. So, today I'm much more about just going to go through the first part of the content, sort of setting the scene. I just lost someone. So that's what I'm going to do and show you some maple, etc. as well. So I guess before we start anything, just looking at how to run this sort of meeting, etc. So you are more than welcome to ask questions whenever you feel like in the chat box. And I can see lots of people already worked out how to use that. That's great. If you want to, you can stick your hand up as well. There's a little, so at the very top of the page, you can stick your hand up. So you can, if anyone wants to speak with the microphone, I can. I think everyone's got microphone rights. It's fine just to use the chat box too. So I've given people microphone rights. So if you feel like speaking on a microphone, if it's easier to speak to me, go ahead. You can always use your chat box to talk instead. So I said I've got some things I want to cover, but this is to be. You realise, as someone just worked out, you can turn the microphone on by pressing the icon towards the top, but it does get feedback if you're not careful, and you just click the microphone icon a second time to mute it when you don't want to speak. So, by all means, this is a chance for you. So, please ask questions you need to. Everyone's getting it worked out. That's good. Awesome. So, overall, what's the subject about? So, essentially, the subject really is extending the ideas of calculus, so differentiation, integration, to functions of many variables. That's pretty much it. That's all over. So, the first third of the subject, approximately, we'll look at extending differential calculus. Sort of what we're looking at, and we'll do more of that from next week, admittedly. The middle section of the subject is looking at extending integration to functions of many variables called multiple integrals. And then the last third is extending the idea of calculus, both differential and integration, to the idea of vectors. And that will pull things that we've done earlier together. So that's a really simple overview. In order to start the ball rolling nicely, we need to just have a bunch of objects that we're going to do differentiation and integration over. So normal integration and differentiation really is just doing it 1D functions. So just functions, just a curve on a plane, XY plane. And so what we want to do here is, instead of iterating over an interval, effectively what it really is, we'll integrate over curves, surfaces, and that sort of stuff. So we're going to have a building block. So that's what I'm going to focus on today, just on these building blocks. So the first of these are curves, and the second building blocks are surfaces. So curves, which would have to live in at least 2D, but they can live in higher dimensions too, are basically the first thing. So the simplest curves you can have are straight lines. For the sake of time, I won't do it today, but hopefully you know lots about straight lines, but they are important. So you revise them if you need to. The next most simplest are called conics. And that's the general form of the equation you can see in the slide here. And again, if you need to, on this main window, depending on your device you're looking at, there's a little icon towards the top right, which allows you to full screen, if that makes it easier to see on the big screen. And if it's too small, again, just give me feedback. I zoom in and out quite easily. So this is a conic. Conics pretty much have the highest sum of terms where the terms are either quadratic or linear, or constant, as the case may be. Now there are three main types of conics, which I'll go through one at a time. There are some degenerate ones like points and straight lines, and even nothing at all. So we'll skip those simpler ones today. The other thing to say is that in full generality, that you can do conics in all sorts of formats. We'll focus on, I guess we'll call the simpler ones, where the the axes of the conic align with the principal axis, so x and y axis primarily, make it a bit easier. So a few things with conics. Ultimately, I'm trying to build up towards high dimensions, and so I'm really concerned with the idea of surfaces. And so in order to be able to do a surface nicely, you need to decompose all its conics and work them out nicely. So I want to have quick ways of classifying conics. That would be really helpful for us. That's for one thing. So although we want just an intuitive, broad understanding about classification, it's still useful to draw them, and a few details are important. So I'll give you more than we need, and I'll just talk through the more critical ones. So the first type of conic are ellipses, deformed circles essentially. So here's got some nice pictures. So you can see ellipses all the time in sort of branding, like Batman over here. So other applications of ellipses is, say, orbits of planets around the sun, or about satellites around the Earth, often elliptical orbits, which Kepler worked out. This top image here this is something from work that I've done in the past, that ellipses are really useful for modeling. So this is a human silhouette. The yellow points are just samples from this silhouette. And you're trying to work out from the silhouette, a human pose essentially, and you can sort of give a rough skeleton of a person using a bunch of ellipses. Ellipses are good because you can stretch them out to be really thin, so they have a sense of different dimensions, and they have a clear joint structure, but nevertheless, they're still really simple. So from a mathematical point of view, they're a nice way to model stuff. And this is based on, depending where you've done it, using the normal distribution as an artifact. So it's using a 2D normal distribution for each ellipse. So it really has nice modeling properties. So they're good stuff, I guess is what I'm trying to say. Here's an example, which I'll have a go at drawing in a second. So ellipses, really in simple terms, are, when you look at them, look like sum of squares. That's how you would normally recognize them in the first place, and that's a key way of recognizing them. In practice, what I would normally do for an ellipse is first just recognize, balanced ellipse, sum of squares. If you've got lots of other terms, I would complete this square first. It's not required in this example, and that will help you, and go from there. So how about I scribble a bit, and I'll talk about a few more things as I do that. And again, if I'm writing too small or anything like that, let me know. If you want me to slow down or whatnot, again, let me know as always. So you can type or you can just talk as well. So first thing I would do for an ellipse is complete the square like it's already done. Then when it's complete square, it's just a sum of squares. Then I want to work out the vertices. That's really helpful, again, just to get a detail for it, but just to give a good sense of drawing it too. And what I would do that is to basically let each part be 0. So this is the first square. So I'm going to let x be 0 is my first bit. So essentially, I would sort of just cover it up how I would normally think about it. And so what I'm left with is y squared on 25 equals 1. And so what does y equal to? I'll let you guys answer the question for me. Just type in the answer in the chat box is the easiest way of doing it. Yep. So you get 5, or minus 5. Yep. So you get 2 answers. And so you can see that x equals 0 and plus or minus 5 are 2 vertices. The second time, you let the next square, in this case, y be 0 as well. And so we're getting x squared plus x squared on 9 equals 1. And so what are the possible x values? Yep, plus or minus 3. And so they form the other 2 vertices. So now I've got the vertices, I can now draw a picture. So you've got 1, 2, 3. That's the first one vertex here, 1, 2, 3. another vertex, and up 5. Hopefully I haven't quite done this. So by just making both of these squares 0, you can quickly work out what the vertices are. Now, because this is a simpler one, where the center is the origin, it's easier. But if it's completed, if the squares be completed, the square might be x minus 1 all squared, for example. But you let that whole term collapse to 0 to work out what the vertices are. So now you've got the vertices, pretty much it's just joining the dots into make an ellipse. And that's much easier done on a piece of paper than it is on a screen, unfortunately. But you know, smooth it out a bit. I'll show you a better version. I'll show you a better version of the picture in a second. But that's the ellipse just there. And the key things to note, really, to label it is the center, which in this case is the origin, and the vertices. To work out where the center is, if you complete the square, it's just when both squares are equal to 0, or pretty much where the full vertices line up. So other things which is useful to label for an ellipse are what's called the focal points. So you look at the direction. So you got one direction's got a length of 5 and the other length of 3. So these axes here are called, so the long one is called the major axis, half it's called the semi-major axis, you want to use fancy names, and the short one is called the minor axis. So you've got to work out which one's the big one. So in this case, 5 is bigger than 3. So along this major axis here is the focus. And to work out what the focus is, you basically take the long direction, in this case is 5, square it, then subtract off the short direction, which in this case is 3 squared, and then take the square root. And that gives you the distance along this major axis of where the focus is. So 5 squared minus 3 squared is equal to what? Again, keep you guys engaged, hopefully. Yep, so 4 or minus 4. So 4 along here will give you the focus. So this would be focus 1, and again before below in a similar way. So we've got 2 foci. And that's the basic way of doing it. So long direction squared minus short direction squared, and then take square root to give you the possibilities. And that was a simple way of labeling it of an ellipse. Just want to show you how you do this sort of stuff in Maple. So in Maple, to do the more fancier plot options, you do with plots, like that. And then you want to do, it's called an implicit plot. And then you type the equation in, which was, remind myself, x squared on 9 plus y squared on 25 equals 1. And then you just go, x is from, we know the answer, so minus 3, y equals minus 5 to 5 are the vertices. Now that looks a lot like a circle. Just to make it really clear what it really looks like, if you go scaling equals constrained, you can see that looks a bit more like what my picture was supposed to be. So an ellipse. And you can do other fancy things to put labels on it for Maple. So in your assignment, assignment 1, you have to draw some pictures from time to time. You can free draw them like you probably will in your exam. It's sometimes easy to use Maple to help you out. Maple's certainly not the only way of drawing graphs like this. And you're still not constrained to Maple, but this is, I think, useful at times. You can see the problem with any computer program is it doesn't necessarily label it for you nicely. And so you have to do some more stuff to it. So that's just a quick crash course in ellipses, essentially. So I will put these notes that I'm showing you now up with the recordings a little bit later on, and you can see that the Maple code that I've just typed in is at the top there if you need to. If you are going to copy and paste this later, the carrots, those little hat things, don't copy from a PDF properly into a Maple, unfortunately. So you'll have to free type them, but everything else it's all right. Okay, so that's the first conic type. Next one is hyperbolas. And like an ellipse is like a sum of squares, hyperbola's quick way of seeing them is like a difference of squares, essentially. So again, can't spell there, obviously. Got a different spelt wrong. But examples of hyperbolas is this thing here. This is a cooling tower at a power plant. So where I live in Orange, you see them when you're driving to Sydney from here. You see them at Warrang near Lithgow. These big towers, and the sides here form a hyperbola. Pretty much just a hyperbola spun around. This particular shape, which we'll look at later, is a hyperboloid of one sheet, or a circular hyperboloid of one sheet even. So this is one of the surfaces we'll look at later. But you can see the hyperbolas cropping up. You also get hyperbolas if you get a lamp and you put it near the wall. The sort of glow, I guess you call it, from the light will form a hyperbolic shape on the wall for you. Shadow's the wrong word, but yes, it's the glow from the light. And other sort of projections like that on a flat surface also give hyperbolas for you. There's other ones. So, I mean, hyperboloids of one sheet are great because you can form all from straight lines. It's a tangential property for it. And so things like there's hyperbolic gears and things like that as well, which it uses. So looking at an example, this one here. So this is an example of a hyperbola. And again, in order to classify it, first of all, I would complete the square, which has already been done in this case. That's done. Once the square is completed, when you see the difference of squares, again, that immediately suggests, oh, it's going to be a hyperbola. So again, you need to do that quick classification. So sometimes you just need to know what it is, rather than how to draw it quickly. You just need to go, I just want to know it's hyperbola. Once it's a hyperbola, again, we want to try to draw it. Now, these are a little harder to draw because you just need more than just the vertices. But we'll start there nevertheless. So same trick as we did before. We'll start with the vertices. And so you'd let the first square, so you let the squares be 0. So I'll just talk about the first one. So if you let the first square be 0, you're getting minus y squared on 16 equals 1. And if you try that, you're going to get no answers because you've got a negative number equals positive 1. So there are no real answers. So that doesn't work. So you can see you won't get as many vertices for a hyperbola as you do an ellipse. Same trick. We'll still let the other one be 0. So if y is 0, we'll get x squared 9 equals 1. And that implies that x is equal to what? Yep, plus or minus 3. Thank you. And so we have vertices, just only 2 of them in this case, plus or minus 3. And the curve's going to touch through that. So we'll draw it in the second way. Hyperbolas basically have an asymptote as well, and they are really helpful to draw it. And so when you've got a difference of 2 squares here, what I would do is factorize it. So if I just factorize this form, so it's the x squared on 9 is x on 3 all squared. So you just take the term. So the difference of 2 squareds is the difference of the numbers, difference of the quantities, times by the sum of the quantities. Is how you factorize the difference of 2 squares. So that's exactly the same term, and I haven't changed anything at all. But when each of these factors here, they can't be 0, because if they were 0, you can't get 0 times something gives you 1. So both of these factors can't be 0. So the asymptotes then, which are lines which the function never is equal to, but you can make it as close as you want to, is when each of these curves, so both the plus and the minus case, are equal to 0. So let's have a look. So we got 1, 2, 3. So that's our 1. So there are our vertices that we know. And 1, 2, 3, 4 is the sort of other number we've got. And there's no. And so then these curves here, so x on 3 plus or minus y on 4 equals 0, you can rearrange these. So this is y is basically plus or minus 4/3 on x. So when x equals 3, depending which one you're looking at, y is either equal to 4 or minus 4. They're two different asymptotes. And when x equals 0, you get the origin. So basically, they're both lines, straight lines passed into the origin in this case. From there. So these are the two asymptotes. This is the y equals the plus 4 case. And this is the minus case. So that's the asymptotes. And then to draw the curve, need a bit more space than what I've done here. Get a nice color. So you start at the vertex and you move closer and closer to the asymptote. Like that. And same on both sides. And so this green curve here is the hyperbola. So just recapping, to notice a rare hyperbola in the first place, you see there's a difference of squares. Then in order to draw it, make each square 0, and you quickly work out you'll get 2 vertices cropping up. That's your starting point to draw it. Then factorize the difference of 2 squares. Each of these factors equal to 0 gives a straight line, which form the asymptotes. So draw them as well. And then just draw the curve so that it passes the vertex and gets closer to these asymptotes as time goes on. So just like the ellipse has focus, so does hyperbola. And again, it would be on the same line as the, what do you call it, vertices are on. And it's, instead of being between, it's going to be on the outside, so somewhere over here. And how you work them out is you've got 2 numbers down the bottom here, and you want to get something bigger, so you just get the sum of these 2 numbers. So that's the length 3 squared plus 4 squared, and take square root, gives you, in this case, 5 plus or minus 5. So the 2 focus would be plus or minus 5. They're the foci. But to draw it, asymptotes and their vertices are really critical. Again, I just want to show you in Maple how to do that. A bit bigger. So again, it was x squared on 9 minus y squared on 16 equals 1. It gets a bit bigger, so I'm just putting a different range for x and y. Now again, if you don't know much about Maple, just ask. So same sort of things as before, and you can see that's the nice hyperbola. You can do some fancy things with Maple, which I'm going to do. So you can have 2 plots overlay. So you do P1 as a sign of the first plot. It's easy to put a colon at the end rather than a semicolon. I'm pressing Shift Enter to be able to type more than one thing in one line. And I'm going to plot just a normal plot. I'm going to plot the 2 curves, which we know is 4 on 3 times by x, and minus 4 on 3 times by x are the ones we worked out. X equals minus 10 to 10. And then to put both of them together, you do display and then the names of the two curves. And to make it look nice, I'll just do the color. So color equals green to make it easy to see. So you can do some pretty cool things with Maple here. So you can see that the green curves are the two asymptotes that I drew earlier. You can see that the vertices are still -3 plus -3. And you can see that the curve gets closer and closer to that asymptote as time goes on. So that's so the computer can draw it more accurately. It misses qualitative features at times. So it's good to be able to understand it from being able to sketch it on a piece of paper. So both are important. And again, I've got that noted down on my little slides here if you want to look at it later, that sort of code. So the last of the conics are parabolas, and where the ellipses are sums of squares and hyperbolas are differences of squares. Parabolas are when there's a mixed amount of terms. There's both quadratic terms, so square terms as you call it, and linear terms mixed together, and it can't be resolved in just squares alone. So you see parabolas in the harbour bridge, like lots of arch bridges. So the bottom arch here is a nice parabola for the harbour bridge. The top is not quite, it curves out the end there a bit, but it's close. And the reason for a parabola in an arch bridge is it distributes the weight nice and evenly across the whole structure, rather than making a 1 point stress more than everything else. You see parabolas when you throw objects in Angry Birds, even, I guess, in parabolic mirrors and headlights and halogen lamps, etc. So there's lots of examples. I'll show you some pictures later. So let's look at one picture. Now, you've probably seen more parabolas than anything else, so that might be simplest for you. But I just want to show you some of the ideas. So when faced with a more generic conic like this, and you can tell it's a conic because it's just a sum of quadratic and linear terms, which in this case is. First thing, there's lots of terms I would complete the square. So in this case, you notice there's an x squared and an x term. So I really want to group them together. So let's put all the x squared terms together, x terms together, and all the y terms together. And for the moment, just leave any constants by themselves. So in order to complete the square, when you've got a perfect square, let's do x minus a all square for the moment. If you expand that out, a is what we really want to know, then you end up getting x, make it plus even. So if you do x plus a all squared, you get x squared plus 2ax plus a squared. So to work out this a, what we need to do here is we need to look at the coefficient of x, which in this case is -4. We need to halve it, it shouldn't be a 2, get rid of the 2, so you get -2, and that tells you what the term we need here is. So it should be x minus 2 all squared. Now I haven't quite got it right yet, so we need to fix ourselves up. So if you expanded x minus 2 all squared, you get the x squared, great. You get the -2x times by 2 to give you the -4x, awesome. But it also gives an extra term. It gives you a +2 squared as well. So we need to subtract off this 4 to make them equal. So this is the trick of completing the square. So I said, look at the coefficient, divide by 2, that gives you the number in here. And then just subtract off or add a constant, or normally subtract off a constant term to make sure the whole thing balances. Then leave the y by itself, and 3 and then equals 0. So if you've got 2 squared terms or 3 squared terms, when we look at surfaces later on, you would complete all of the squares at the same time. Then once you do that, bunch all the constants together. So you've got -4 and +3 gives you -1. Now, if you only got square terms, you might have a constant term by itself. But if you got a linear term, like we have in this case, I would just bury the constant with it. So I would just put this in brackets. So my sort of completed format is x squared minus 2 squared plus y minus 1 equals 0, or putting another way, y minus. Hello, am I still there? I just dropped out, I think. Okay, good. It just dropped out and lost my microphone briefly. Okay, sorry about that. So as I was saying, I'm not quite sure when it dropped out. That I've just put the y term on one side, and the reason. Okay, good. Thank you. So as I was just trying to say is, I put the y term on one side mostly because for me that's the form of a parabola that I'm familiar with from a long time ago. You can pick a form that you're familiar with. So once you've completed the square, then you can easily see the, I guess we call the center of it. And this is true for ellipses and hyperbolas too. So when this is equal to 0, you get the center. So y equals 0. And when this is 0, x equals 2, that gives you the center in general. So y equals, when x equals 2 and y equals 1, that'd be the center. Now, for an ellipse or a hyperbola, that really is where the middle of the two foci, and that's where the axes will overlap, etc. For a parabola, that also happens to be the vertex as well. So center is the wrong word for it, I think, really. So it's really the reference point for it all. It's all the origin, so to speak. So in this case, for a parabola, it's going to be the vertex. Now, what you need to know from then is, so parabolas always look like smiley faces or frowns, or spun around somewhere or other. You just need to know where does it go from here. Does it go up or down, etc. And you can do it by typing in a few test cases. More formally, when it's y is equal to positive x squared, it's going to be a smile. When it's y is minus x squared, like it is here, it's going to be a frown. Something like that. And I haven't really bothered to work out what the intercepts are properly here. I might need to in an application. In this case, I'm not really worrying about it. But just getting the sense of the direction, that's the main thing. If it was x is equal to positive y squared, it'd be on the side. It would be looking on the side over here. If it's x is minus y squared, it'd be the other direction. So there's all different sort of shapes. So that's my quick drawing of a parabola. So for a parabola, I guess the key things really label is, we need to know a sense of where this vertex is, pretty critical, and also the direction it's facing is probably the most important things for labeling. I guess what the other thing I want to show that last sample is the idea of completing the square, which is really important for many applications. So that's the quick rundown of conics. And I'll skip the maple for that one, unless you want me to show you. So conics are really useful because they end up becoming the slices or building blocks even of the more complicated surfaces we look at. And so when trying to understand surfaces, it's really important to be able to decompose those into the simple stuff and be able to recognize them quickly. That's why I want to stress, just saying again, ellipses are really sums of squares, hyperbolas are differences of squares, and parabolas are a mix, so a quadratic term and a linear term. And that's a quick way of recognizing any of them. So there's a few more things with conics, and we'll see some of them as we look at in a second. So curves are good, and they are nice things in 2D space, but we want to be able to understand surfaces as well. And these are things that live in 3D, and technically they're 2D objects. So what I mean by that is, if you're sitting on the surface of a sphere, like we do in the world, planet Earth, there are two directions you can go, either forwards or backwards or left and right, when you stay on the surface. So there's two fundamental dimensions. So it's a two-dimensional object locally. So the simplest surface is certainly a plane, which you've hopefully have seen of some before, so I won't talk about more about it. The next one, planes are important, don't get me wrong, so please make sure you understand them. The next ones, which are more complicated and therefore worth spending some time today to help me nut them out, are quartics. So pretty much, they look a bit like conics at first glance. They're pretty much, instead of having, they still have lots of quadratic terms and linear terms. So lots of quadratic terms and linear terms. Except instead of being in two variables, they have three variables. Hence the idea of living in 3D. And these quartics include many types of surfaces. They include some what we call degenerate cases, which are cylinders, including this classic circular cylinder, but they include other sorts of cylinders. So cylinders is a more generic word, and things like spheres as well. So there's sort of special cases, I call it. There are some fundamental different types of quartics though, and you can sort of classify all the main types. So just going to focus on this example in a second. And I will, if people have questions, I can do some more of this sort of stuff next week as well, if you find it, if you would like, it's okay. But I think it's good today just to give an introduction to how you do approach some of this sort of stuff. You can see what I was rapping on before, and then go from there. And if you need to do some practice questions and you still don't get it, which I'm sure will happen, some of this is a bit tricky to understand. Again, ask next week. So as I said before, the purpose of these sessions is to help you guys out. So what I want from in future weeks, I will give certainly frame some of the content, but I would like to have spent some of the time answering questions that you guys really want in this sort of broader area. It can be recorded, and even if you're watching this later being recorded, not just the people attending live, I'm happy to answer your questions too, for that matter. Just make sure you ask a question and you can watch the recording. Okay, so let's look at some pictures of some of these surfaces. So these quartic surfaces are some sort of form some classic surfaces you see from time to time. So one is called an ellipsoid, which pretty much is a football. So it's an NRL football. And what's so special about all these is if you take the cross sections, so if you sliced up this football in different directions, you get either circles or ellipses. And so if you slice it up, you get the conic sections. And depending on how you cut up, you get different slices. Different slice types really determine the name of the object and what it is. So if you can slice it in two different directions, like this one, so slice it, as I'm seeing it, left and right and top down, two directions to get ellipses, then it's called an ellipsoid. This is called an ellipsoid. Here's another one. This is halogen light. So the surface in question is the inside of the bulb here. So if I took cross sections from top down to the bottom, you'd actually get a parabola. So it's the cross section here is always parabolas. If you take it horizontally, you also get parabolas. So you get parabolas in two different directions. So this is called a paraboloid. It's a fancy name for it. And because the third cross section are circles, it's called either an elliptic or a circular paraboloid. So elliptic paraboloid is a more generic term. And so you got lots of these cool surfaces that you can crop up. A hyperbolic paraboloid, again, if you take cross sections in two different directions, you get parabolas. The third one's hyperbolas. So you got lots of them. You get the funny cone, and the other one I've seen is the hyperboloid of one sheet. There's one last key example called a hyperboloid of two sheets. I had a little bit more trouble finding an image of seeing that in real life, but I always think of that as being like a stalagmite down the bottom and a stalactite at the top, trying to join together. So let's look at, before giving more details, let's just look at how you try to handle these sorts of things. So firstly, when you see a surface like this and you go, I want to try to understand it, I want to try to draw it, so I'm going to try to sketch this thing. So a few things, I like to be able to classify it, work out what type of surface it actually is, and also I want to be able to try to sketch it. That just shows you a simple understanding of it. So first thing I would do is try to complete the square. In this case, it already is. So all the square terms have no linear terms with them, so it's already completed. Second thing, you can, after a while, learn some key special forms, and you might go, when there's a sums of squares and difference of squares, etc., you can start working out some standard forms, and you could utilize that if you wanted to. On the example formula sheet, which is embedded in the study guide, and you can see the Interact 2 site, it has some of those standard forms there, which you might find beneficial. I find that because the standard forms, sometimes get muddied up when you swap roles of X's and Y's and stuff like that, I much prefer the concept of using traces. Trace is the idea of taking cross sections of this surface for different along the different planes, key principal planes. So what I'm going to do is I'm going to let X here be a fixed number. Now I want to consider all possible cuts. So it could be X equals 0, X equals 1, X equals 2, X equals 3. So I'm getting all the different cuts at once. Because I don't want to do just one of them, I'll say X naught to say all of them at the same time. So I'm really thinking as X as being fixed at this point in time for the different cuts. So when I do that, all the terms not involving X, just leave them as they are, but then dump all the X terms on the other side. Positive to make it more correct. So pretty much what I've got is on the left-hand side here, I've got variables, so Y and Z are still varying. And on the right-hand side, it should be just a constant. So if X naught was 1, it'd be 2, for example. If X naught was 0, it'd be 1, etc. So it'll be just a constant depending what particular slice you're taking. So what this really corresponds to is slicing up the object in different ways. So then I want to know what type these slices are. So here, this is going to be a conic now, most of the time. What sort of conic do we get? So the options are hyperbola, ellipse, parabola, or degenerate. And there's someone that's got there, so thank you. This is an ellipse. Now, at first pass through, it's easy just to quickly say it's ellipse. And the reason why I'd say that is because you've got a sums of squares. That's how I'd say it quickly. Sums of squares, ellipse. On the second pass, sometimes it's good to realize there are a few degenerate cases at times. So this is only an ellipse if what's on the right-hand side here is a positive number. So if it was negative or 0, it's not an ellipse anymore. So if it's equal to 0, you get a point. If it's a negative, you get nothing. And it's important to notice that. In this case, that's always positive, which is what yeah, so it's sometimes when you do this, you'll get the answer, say this is negative, and you go, well, that means that slice does not exist. There is just nothing happening there. So you're right. It has to be positive for it to be a real slice. So if we go back to our football, for example, so if you take slices through the ball, you get ellipses. But if you start taking a slice for an X value too big off the edge of the ball, you'll end up getting nothing. And how you see that is that when you do that, you'll get a negative number on the over side, which suggests there really is nothing there at all. So it's important to do that on a sort of second pass. So we do the traces for the other directions too. So all three principal directions. So again, with the Y's, you just leave all the variables on one side and dump all the constants that we have on the other side. In this case, the constant is the Y term. And again, this is a constant. So what sort of conic is this one here? So a few people have got, so it's a hyperbola. And the reason why you can tell it's a hyperbola is because there's a difference of squares. And then you work out the last direction as well. Again, this is my first pass, just doing it simply. I've got minus x squared plus y squared are the other variable terms, leave them as they are, is equal to 1 minus my now constant z value. And what sort of conic is that one? Yeah, so thank you very much. So hyperbola, as someone's got, it's great. So when you've got traces in the 3 different directions, you can then work out what it is, or mostly. I'll spell that out. So if you have two different directions having the same type, like we have here, and that's always happens. So you can always get 2 different directions will be the same type. So you get 2 hyperbolas. So as soon as you see that, then you end up getting a that sort of shape, and you just make it a hyperboloid. So if it was 2 ellipses in 2 different directions, you'd get a ellipsoid. If it was parabolas in 2 different directions, you get some sort of paraboloid. The trace in the other direction gives you information about what type it is. So for example, if it was a paraboloid, the other direction would tell you what type it is. So it'd be an elliptic paraboloid or a hyperbolic paraboloid, for example. The special case really is these hyperboloids. This is the funniest cases, but still, this direction, this last trace, the ellipses do give you information on what's happening. So for hyperboloids, all hyperboloids, the cross sections always end up being ellipses. That's always true. So they're all elliptic hyperboloids in that sense. But you can get 3 sorts of cases happening, and this is where you need to go back and look carefully up the top here, which I can see some have worked out already. So you need to think, is there any gaps? So are they always ellipses? So in this case, this term here is always positive. So therefore, we'll always get an answer. We'll always get an ellipse. So this is this sense that we'll get ellipses all the time. So this hyperboloid is called a hyperboloid of one sheet. Is the answer? Someone's remarked. So pretty much, everything's always connected. On the other hand, if there was a gap, so if there was some values that you just won't find any trace at all, that means there's a break in the whole surface, and to be broken into 2 parts, it'd be called a hyperboloid of 2 sheets. And the last case, which is sort of right bang in the middle, is when it shrinks down to a point at one special place before it grows up again. That's called a cone. So this is a hyperboloid of 1 sheet. Let's just draw some pictures of what I was talking about. So traces in 2 directions are hyperbolas. So in the 3rd direction, we have 3 options. Ellipses, no break. Ellipses, except, I'm writing terrible day, sorry. 1 point. And ellipses with a break. So to give you a sense what they all look like. This one we've got here. So this one was, let's write down what we've got. So z squared minus x squared plus y squared and 4 is equal to 1 would basically, okay, don't know what I said wrong. That's basically equal to that's an example of an ellipse with no breaks. If you've got another case almost the same curve, but is equal to -1. This case here, when you expand it out, you'd end up getting -1 plus x naught squared. And sometimes what happens is that will give you a negative number. So there will be some times when ellipses don't exist, and therefore that forms the break. So you'd be back to the same, except that would be minus. So yes, we get negative numbers sometimes. So in terms of what they look like, so the first case pretty much looks like a hyperbola, but just spun around in a big circle. So like that cooling tower we saw before. So the cooling tower is an example of this, just cut off in the middle. The third case is again a hyperbola like this, but spun around the other way. So when you spin around, there's a big gap in the middle here. And so this is first, number one's called a hyperboloid of one sheet, and this third case is called a hyperboloid of two sheets because there's a big gap, so two pieces to it. The case in the middle is a separate one, is when there is not a gap as such, so there's no break, but it reduces down to the degenerate case right in the middle, and that's when you get equal to 0. So you've got no constant term at all. What that looks like is it's a cone, so just a double cone. And again, if you looked at this sort of cross sections, that'd be equal to x naught squared, and that is never negative, so there's no break, but it does collapse to 0 at a single point, and so you can see that it will collapse down to just a single point bang in the middle here, and that's sort of the degenerate nature. Whereas you can see the hyperboloid of one sheet always is fat the whole way through. There's never a time when it flattens down to a single point. So in answer to Candy's question, to work for hyperboloids, you first recognise the hyperboloid in the first case by two hyperbolas in two different directions, and then you use the third direction to work out which of the three types it is possible for you. And that's how you sort of classify it. I'll draw it in a second, but let's just, before I do that, let's go back to this as my little summary. So you've got down the bottom here, the three different types of hyperboloids. And as I said, it's really going to be that the third direction you're going to work out which type it is. For paraboloids, there's two types. Again, you'd recognize it from having parabolas in two different directions, so you recognize the first place. And it's the third direction that determines the type, whether it be elliptic or hyperbolic are the two possibilities that arise. And the other case is an ellipsoid, and as soon as you get ellipses in two different directions, then it ends up being an ellipsoid. And the third direction has to be an ellipse as well. So they're the easiest ones to spot. They're just sums of squares in the first instance, so you might recognize the standard form straight away. So that just gives you some idea of classifying. So all I've done is classified it so far. Next thing I want to do is try to draw it. So I want to try to sketch it down. So there's different ways of doing that. In an assignment, you can get the computer to help you out, of course, to try to draw some of these things, and I'll show you in Maple briefly. But how I actually draw it is I actually draw the shape first. I know it's a hyperboloid on one sheet, so I would either from a memory or just from a piece of paper, like in an exam, you're allowed a formula sheet. You can just draw a picture of what it looks like. That's my that's the shape it's going to be. Now I just need to label it to make it match up to everything. So what I would do is I'd work out what the center is. Bang, right here. That's sort of the center or the reference point, I guess you want to call it, of the whole object. That's if you've completed the square, that's when each of the squares is equal to 0. In this case, it's already completed. So when Z and X and Y are all 0. So that actually happens to be the origin in this case. So the center is the origin. For a more complicated example, which you'll get in your assignment, you'll have to complete the square to work out what the center is. But then from there. Next thing is I want to put the axes in. So there's going to be an axis bang here, which is the middle of the rotation here, and then 2 perpendicular to that coming out. And I just want to work out what they are. So which one, and this is a simple case, so they're going to be the X, Y, Z axes, is what I've just drawn, but which one's which? And again, this is where your traces come in handy. So the fixing X's basically led us to the different ellipses. And that's a special direction. That's the one that goes up and down. So the one that goes along here, the one that goes the ellipses, is the one that the top down, as I've drawn it at least, axis. So if you do different fixed X values, if you slices that way all the time, and they would get the ellipses again. That's the X-axis. The other 2 directions would be the Y and the Z. So that's my very simple drawing. So what have I not really covered so well on my picture is the fact that the coefficients of the Y and the Z are slightly different. So I've drawn it to make it look like it's a circular hyperboloid of one sheet, but in reality, because you've got a y squared on 4 here, it's actually going to be fatter in the Y direction. So you could have another go at trying to draw that if you can. It gets a bit harder. So in order to do that, I would draw an ellipse for my cross sections all the time. And then just try to draw it, link them up. That last one was too quick. So that's my revised picture. So it's still X, Y, Z. It's an X, sorry. So you got X, Y, Z as per normal, except that the fatter direction of the parabola is in the Y direction. So that's how you do it by hand. Let's do it by computer. So if it's by hand, what I'm looking for is qualitative understanding of what the thing looks like with some clear labels to know what this particular instance is. So in this case, I eventually realized roughly what a hyperboloid of one sheet looks like, and you need to know enough the location, so center, and the orientation only given by the principal axis. So if I completed the square and the center is not through the origin, I would still draw axes like I've gone through the center, and it will be like X equals 1, Y equals 0, and whatnot. Oh, sorry. This axis here would be Z equals 0, Y equals 0, what it should be. So I'd still draw it in a similar way, to tell the truth. So let's finish off by looking at Maple. So to draw something like this, again, you have to have the width plot to the very top, and it's implicit plot. And this time I'm going to do it in 3D. I'm going to do the function. So it's Z squared minus X squared plus Y squared on 4 is equal to 1. And then just pick some ranges. So minus 10 to 10, Y is equal to minus 20 to 20, and Z is equal to minus 10 to 10. So just picking some arbitrary numbers. And just so I can see that it's not a circular, but it really is elliptic, I'm going to put a scaling equal constraint to make it look better. So that's the picture. The problem with Maple is that when it does the drawing, it only picks a few points. And you've essentially got a gap there, which is a pretty bad picture. So what you need to do sometimes is you need to make it draw more points. So if I do num points is equal to 5,000, let's make it lots of them, it will draw it more accurately for me. So And you can see now that's closer what it looks like. So you can see it closes down to a narrow point, but not zero at the here at now near the origin, and then fattens up again. So this hyperboloid of one sheet really is coming down to one point and then expanding out again. So if you put a few more points in, you can sort of see a bit more rounded at the beginning there. If you put too many points, it can crash the computer. So be wary of that. So that's an example of a hyperboloid of one sheet. And again, how you can use the computer. You can see the computer has problems. It doesn't put axes down, etc. You can do a few things while putting options down. In an assignment, you can also right-click, if you don't remember stuff, and ask us to put stuff. So you can do axes. Can I have a box axes, please? Just so you got some labels for it, etc. And you can type it in commands, but I think sometimes just the menus up here, adding a title, etc. might help. So in your assignment, when it comes to working out these sort of stuff, you're probably going to need to label it. And in practice, it's probably going to be easy for many of you just to print out the picture and scribble over the top of it, or import it into Paint and scribble over the top of it just for the labeling. And in this case, as I said, center is really critical, and some idea of the orientation of this shape is what I'll be looking for labeling. So it doesn't no precise thing I'm looking for, but orientation and the center would be the real critical ones. So that's a real quick introduction to surfaces. So a real quick introduction to conics and to the quadratic surfaces. So that's really the quick introduction I've done so far. So please go away, try, read up where you have needed to. I mean, it's only second day, so you may not have read much. So make sure you read through, say, the first 5 sections of the 1.1, 1.5, the study guide, and try some questions from tutorial 1. So what I would like to do next week is I'll look at questions from tutorials 1 and 2. That's what I want to focus on. But I want you to think, well, what do you need more help with? So I'll also have some things in mind, of course, but what questions do you have? And quite possibly I'll do some more of this here. Okay, so I've got one question. So you've got any questions, fire away, of course. So the question I've got, someone's asking, to put an equation of surface in standard form, do you put all the variables on one side and the constants on the other? So standard form pretty much is completing the square. That's what I would normally mean by it. Once you've completed the square, you're right, you tend to put all the variables on one side and the constants on the other. Depends on the textbook. Sometimes they would divide by the constant term to make it into one, to make it super standard. In your assignment, if you're looking at that case, I won't be so fussed by that. It's more the completing the square that I'm more concerned with in that sort of regard. But if you wanted to really compare it nicely to a standard table, that's what we look at. So just one thing, formula sheet, here it is. So this is the formula sheet, and if you can read that from there, you're doing fantastic. On the back side of the formula sheet, there's a table I just presented, but it also has some equations. So here's the equations, just zoomed in a bit more. And you can see these are the sort of the standard forms. And you can see whenever there's a constant, it's always been made into 1 most of the time. The one exception is that, I mean, you probably could do it for 1 of this case here, but that's the hyperboloid of 2 sheets. And I put -1 just for comparison purposes more than anything else. But these are sort of the standard forms. And so you don't have to note if we go that far. So any other questions people have today? I'm more than happy to answer the question today, of course, but otherwise you can do practice, which is, again, how you're going to learn more than anything else. But hopefully there's some demonstration of some of these things that's helped you today. Okay, thanks everyone for coming. I'll just turn the recording off.